Hello, this is Nature Nerd 1000, and welcome to another episode of my number Conlang, Ancient Binary. And I was researching into base number systems and found out that the Babylonians used a base 60 number system. So I was thinking, with ancient binary, is there any possible way to make this like a base 64 or base 60 number system? And what I came up with is a much faster way how to write computer code. And who knows, maybe this could be used or something. Usually computer code is so inefficient to write because it keeps doubling, and you have to write like 5 zeros and like write the ones in the right spot. So is there a faster way to write in computer code? And I'll show you right here. So basically what I came up with is you could double it, and it still alternates like the original ancient binary code. So basically 1, 2, 4, 8, 16, 32, and if you add all these together, it equals 63. So we can do a base 64 number system with ancient binary. And now I'm going to show you how to write it. It's a little bit different pattern than the original one. Yes, Roger there. One, 2, 4, 8, 16, 32. So it's very simple. 0 is a line. 0 is just a basic line like the original ancient binary system. So 1 equals that. See how it correlates. 2. Then here is where it gets different because you have to add all these up. So this is 3. And then on the next one you would go to 4. Then basically 4 plus 1 equals 5. See if I can get this camera better. Yeah, screwed up. Then we just go to 6. 4 plus 2 equals 6. And then once you get to 7, because a line, 1 plus 2 equals 3. And then just add the 4. And as you can see, this is a much faster way to write binary code. Like if you wanted 7 on binary code, you would have to write 0, 0, or actually, try to think. Yeah. 4 plus 2 plus 1 equals 7 in binary code. But with this, we can just write it simple like this. So then, basically, since these are all filled out, we're just going to go to 8, because up here is this middle spot is 8. And then, let's see, 9. 8 plus 1. Then we have 10. 8 plus 2. Kind of like the original, except reverse. And we'll just keep on going. So now since the 3 is filled up, 12 looks like a plus. And I'll just keep on going. 12 plus 1, 13. 12 plus 2, 14. 12 plus 3 is 15. And then since these are filled up, now we go down to this corner. 16. Then 16 plus 1 equals 17. And so on. I'm just going to keep going till base 64. 16 plus 2, 18. 16 plus 3. This is a little bit tedious. 19. It's possible I may make a mistake too. and 20. 16 plus 4, 20. So now we're writing in binary code a much more efficient way, and it's a good coding method, and yeah. Now on 24, we have 16 plus 8, 24. I mean, it's a bit tedious to memorize this, but once you know the pattern, it's actually quite a simple code. Let's go to 26 here. And we'll just keep on going. 28. Divert to 4. 29. 30. 31. So now it's filled up here. So then for 32, we just go up here to the right. And then 33, it's just 32 plus 1, and it just keeps like repeating this cycle over and over again. And it's so cool that we're writing I guess binary in a much more efficient way. And then on top of that, we can use a number system that can go up to a base 64 system, and I'll show you how perfectly it works out with that, where I'm limited down to a 59 or 60 system like the ancient Babylonians and improve it with a 0. And I'll have another lesson on ancient binary code and other bases, as well as some multiplication problems on base 20 systems, and maybe 12, hopefully soon. 35, 32 plus 3, 36, 32 plus 4, 37, 39, and then now it's 32 plus 8, so this is 40. And we'll just keep going up. Up until 7. 42. We have that 12 again. Move the camera back a little bit. 45, 46. 7. And so since we filled up this is 48. This should be good. So now we have 48 plus 2. 48 plus 4. So now since we filled up 7, we go to 8. 56, yep. And now we have 7 more, I believe. Here we go, we have 60. So if we did ancient Babylonian, we would limit it here, and then 60 in ancient Babylonian would basically to be this. But but this system is base 64. But I'm just saying it's compatible with ancient Babylonian, and it improves it too. 61. 62, and then 63. So as you can see, it goes up to 63, and then it breaks 64 perfectly. Which I think that's 64 is a reasonable system. So then 64 would look like that. So yeah, basically this is ancient binary code. It's compatible with the Babylonian system of base 60. As well, it compresses computer code to be written in a much easier way. And it's a good code, and code messages in it or something, and then this is a base 64 system as well. Those and powers. And then I think if basically it would keep going on and on 64 times. So like 64 times 64, you would add another 0, and I think that's 4096. Actually, I'll have to do more calculations on that right now. Yeah, so 4096. If you want another 0, so the 3-digit marker. So basically, instead of 1000 being 4, it's 4096, or like 100 being 3 digits in the decimal system, the 10 system. In a base 64 system, 3 digits would be 4096, and then you would have to go through all that if you kept wanting to count by 64s and stuff like that. I don't know, maybe we could practice. So if we wanted to write, let's say 64 plus 64, it's 8, 12. So basically 128 would then look like this. 128, because this is 2, and then it's 2 times 64. Then just add another 64, 12, put the 1, 9. So then 192 would look like this, because this is a 0. And then it's 64. This is 64. 3 sets of 64, and then four sets of 64 would look like that. Also, it has been decided for ancient binary that basically every three digits, basically instead of putting a comma there, well actually you could do a comma, but basically instead of putting a comma there after, let's look at this for example, so it's 4, you would put a dot. So basically a dot is a comma in ancient binary. Yeah, I hope you enjoyed this video. It's compatible with the ancient binary base 64 number system, and yeah, base 60 is pretty cool. Like, they use it in 60 minutes an hour, Yeah, 60 seconds in a minute. Yeah. I just thought that's pretty significant, and I just wanted to challenge myself to make a base 60 or 64 number system. And this is Nature 1000, signing off.